Hello students, welcome to another session of online class. Today in our today's lecture we will be discussing about applications of Laplace equation. So in the last class we have studied what is Laplace equation and Poisson's equation, and we did the derivation for Laplace equation. Poisson's equation derivation is not required. So Poisson's equation, it was del square V is equal to minus rho V by epsilon, and whenever there is a case where rho V is 0, then that is the special case of Poisson's equation, del square V is equal to 0, where del square V is the second second gradient of the scalar V. So this Laplace equation has a significant applications in different fields, especially when solving the problems related to parallel plate capacitors of different configurations. So we know that del square V is equal to 0 if the plates are assigned so that any one of the component, we know that in Cartesian coordinate system the del square V is dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. So if you place our configuration such that, for simplicity, if you keep along the axis itself, then dou square V by dou y square and dou square V by dou z square are not having the component, so only you have del square V is equal to 0 becomes dou square V by dou x square is equal to 0. Now dou square V by dou x square is equal to 0. Since x component is only there, we can modify it as d square V by dx square is equal to 0. Now something derivative is 0 means that should be a constant, right? So from that we can write dv by dx is a constant. I will call it as a. So dv is equal to a dx. Now integrating on both sides, v is equal to a into integral dx is x plus the next constant is b. Okay. So this is a solution when the Laplace equation is unidirectional. Now let us see the particular case, that is solving the parallel plate capacitor. Before that, generally we will see how to come into the capacitance of any configuration. So what and all steps we require. So step 1 is to solve del square V is equal to 0. So what is the outcome? We will get V equal to what? The next step is, from V calculate E is a vector which is nothing but minus del V, negative gradient of V. So the outcome is the value of E. If you know E, the step 3 is easy, that is you can measure D, which is nothing but epsilon times E. So you got the vector D. Now once you got the vector D, now evaluate D at given surface. Okay, surface. So that is nothing but D surface. Now if D is nothing but flux density, flux per area, and rho s is nothing but charge per area, we know that q by a and psi by a will be equal if and only if the D is normal to the surface. So from this one obtain a n cap, so which is the perpendicular to the surface which we are evaluating. So if you know a n cap, you can measure d n cap, right? So once you go to d n, the next step is assign rho s as the normal component. So once you get rho s, then you can calculate charge, because charge is nothing but surface integral rho is ds, because charge per unit area is rho s, so you will get rho s ds. So once you get q, the last step is easy. We know the relation q c equal to qv, or c is equal to q by v, because q is equal to c, right? So the irrespective of whether it is positive or negative, you have to just consider as mod q by v. So these are the steps we have to follow all the cases. Okay. As an example, the first question is to, or first part is to evaluate or measure the capacitance of parallel plate capacitor. So for that, for simplified manner, we'll consider, we know this is x-axis, this is y-axis and z-axis. Now we are placing a plate at x is equal to 0. Okay, so this is the plate we kept at x is equal to 0. I think I can draw it like this. So at x is equal to 0, you have a plate. Okay, and I am separating it with a small distance d and placing another plate at x is equal to, so what is the value of x here, since I moved a d bit, so this is at x is equal to 0 and this is at x is equal to d. Now if you are connecting this one to a battery like this, so I can say at x is equal to 0, v is equal to 0, and at x is equal to d, v equal to the maximum. For example, if it is v0, v equal to v0. So I have kept the configuration in this manner so that it is easy for us to evaluate. Okay. Now the first step is, these are the boundary conditions. These are the boundary conditions. In the last class I have mentioned about boundary condition. So these are the boundary conditions for this particular case of the problem. So as we said, since this is only in the one direction, the Laplace equation del square v equal to 0 simplifies to dou square v by dou x square is equal to 0, because y component and z components are not there, and the solution, as we discussed, it will be v equal to ax plus b. Now the task is to find the value of a and b so that you will get the complete v, right? So substitute x is equal to 0, what you will get, 0 is equal to a into 0 plus b, which is nothing but implies b is equal to 0. So our equation reduced to v equal to ax. Now what I have to substitute, at x is equal to d, v equal to v0. So I can write at x is equal to d implies v0, because v is v0, a d, or a equal to v0 by d. So finally our expression, the constants are a is v0 by d and b is 0. So our expression v is equal to ax plus b, where a is v0 by d plus b is 0, implies v is equal to v0 x by d. So we have done with the first step, we got the value of v0, right? We got the value of v0. Now the second step, this is the second step. From v you have to calculate e. So from v we have to calculate the value of e. So as I said, e is negative gradient of v, which is nothing but dou by dou x of v ax cap plus dou by dou y of v ay cap plus dou by dou y of dou z of v az cap. So substituting, dou by dou x of v is dou by dou x of v is v0 x by d, right, plus dou by dou y, we don't have any y component, so this will be 0, and dou by dou z, again we don't have any z component in the expression, so it will be constant for the differential, so that will be 0. Now v0 by d is a constant, okay, v0 by d is a constant, this can be taken outside. Dou by dou x of x is 1, so v0 by d ax cap, there is a minus sign is there, so which is missing here, so finally it becomes minus v0 by d ax cap. Okay, so done with the second step, E equal to minus del v. So what is the third step? Third step is to find d. So d is epsilon times E. So to get the value of d, E, d is epsilon times E, and we have E is minus v0 d ax cap, so epsilon minus v0 by d ax cap. Okay, now we have to calculate the value of ds. ds is either any one of the surface, we have either x is equal to 0 or x is equal to d. So one of the surface I will consider, that is nothing but x is equal to 0, so that is d at x is equal to 0, which is remains same, epsilon 0 v0 by d, or epsilon in general case 0 won't be there, 0 is available only in the case of we have, if free space is there, epsilon 0 is there, otherwise it is epsilon alone. Okay, so epsilon v0 by d ax cap. So from this one only the normal component is x component only, perpendicular component is x component only, so I can get d normal as epsilon v0 by d. So whenever d normal is epsilon v0 by d, then rho s is nothing but d normal, which is minus epsilon v0 by d. So once you get the value of rho s, so what you have to do, you have to get the value of rho s is done. So q is surface integral rho s ds. Okay, so q is equal to surface integral rho s ds, which is surface integral rho s is minus epsilon v0 by d, then ds. So minus epsilon v0 by d can be taken outside, so whatever is integral over surface ds. Now which is the surface? Surface is nothing but the plate itself. So if you integrate the surface for entire plate of the capacitor, you will get the area of the plate, right? So instead of that, I can write integral minus epsilon v0 by d. The integral will be s or a. So you got the value of q. The last step is you have to find the capacitance. Capacitance is mod q by applied voltage v0, so that will be minus, that will become plus, so epsilon v0 s divided by d divided by v0, so v0 will cancel, so you will get epsilon s by d. So this is, you might have studied in lower class, capacitance is epsilon a by d. So a is the surface area, so here it is different, notation is different, s is there. So this is how you get the value of capacitance from Laplace equation. This is in the case of parallel plate capacitor. Now what we have to do is, we have to use another case. Okay, so we'll use here cylindrical capacitor. Okay, so we have a cylindrical capacitor. So you have two cylinders of different radius, one inner cylinder and another one outer cylinder. So one of them is charged with a negative potential and the other one is charged with a potential. So like this it is connected. Inner is given positive, the outer is given negative. So this is having a radius A and this is having a radius B. So boundary conditions are rho equal to A and rho equal to B, because rho is the thing which is used in the cylindrical coordinate system. So using this at rho equal to A, V equal to, you can say V0 if V0 is the supply given, and at rho equal to B negative supply, so V equal to 0. Remember, B is greater than A. So in cylindrical coordinate system we have three components for del square V. We know this del square V is equal to 0, but only rho component is required, all other components are 0. So rho component is 1 by rho dou by dou rho of rho dou V by dou rho. So all other components are 0, so I am not writing all these big expressions. So this is what you have. So this rho is outside the differential, so you can bring here. So this will be dou by dou rho of rho dou V by dou rho equal to 0. Okay. Integrating for the first time, you will get rho dou V by dou rho is a constant, because differential is 0 means this will be a constant A. So rho dou V by dou rho is A, means dou V by dou rho is equal to A by rho, and dou V is equal to A by A into 1 by rho d rho. So V is equal to, integrating on both sides, A can be taken outside, and 1 by rho is nothing but ln log, natural logarithm, ln rho plus B. So this is the expression you got for A. Now we have to apply the boundary conditions. At rho equal to A, B equal to V0, and at rho equal to B, V equal to 0. So we'll substitute first 0 rho equal to B, so which means 0 equal to A log ln rho B plus B. This is the first expression. And when rho equal to A, V equal to V0, so second equation is V0 is equal to A ln A plus B. So this is the first one, this is the second one. To get the value of A, you have to subtract 2 minus 1. So equation 2 minus 1 gives the LHS V0 minus 0, that will be V0. In RHS, A ln A minus A ln B, so that will be A ln A minus A ln B, and B minus B will be 0, so that will be A ln A minus ln A minus ln B, which is ln A minus ln B will be ln A minus ln B will be ln A by B. So this is the value V0. So A is equal to V0 by ln A by B. Now we have to get the value of B. So from this one you can get the value of B. So B is equal to minus ln A ln B. So B is equal to minus ln A ln B, which is V0 ln B divided by ln A by B minus. Correct? So this is the value of V BC. So substituting the entire expression, okay, what we have, we got the value of B, we got the value of A. So V is equal to A ln rho plus B, which is A is V0 by ln A by B plus B is minus V0, so ln rho is there, minus V0 ln B divided by ln A by B. So here V0 is a constant which can be taken, and denominator is same, ln A by B, and what you have is ln rho minus ln B, which is again log A minus log B is log A by B. So V0 ln rho by B divided by ln A by B. So this is the expression for V. So what is the next step? The next step is, once you get the value of V, you have to get the value of E. E is minus del V. Okay, so del is, we know that the del in the case of cylindrical coordinate system, it will be 1 by dou by dou rho of rho V A arrow cap, right? So if you simplify this expression, so you have plus A phi cap is there with respect to phi, and you have dou by dou z component is there. So these components will be 0 because we don't have any other components, only rho components is left here. So if you substitute those values and simplify, you will get V is equal to V0 by rho 1 by ln B by A arrow cap. Okay, V0 by rho 1 by ln B by A arrow cap. So D is epsilon times V0 rho ln B by A arrow cap, implies ds is equal to d at rho equal to A, implies epsilon 0 V0 by, now rho becomes A ln B by A. Okay. So once you got the value of d normal, that is the component which is perpendicular to A. Now next step is you have to, so that is the rho s. So once you get the value of rho s is same epsilon V0 A ln B by A. So Q is equal to integral rho s ds over the surface So rho s is epsilon v0 a ln b by a into the surface area of the surface A. So what is surface A here in the diagram? Two pi a is the perimeter into length, so 2 pi a l, so that will be the area, right? So into 2 pi a l, so C is equal to q by v. So if you cancel v, you will epsilon 2 pi EAL, so AA cancels here, so whatever left is 2 pi epsilon L divided by ln B by E. So this is the expression for capacitance due to two cylinders. Okay, so we will wind up here for the today's class. We will see other two cases more, so as an application of Laplace equation. Okay, thank you.